Let us consider equilibrium of a body under an arbitrary three-dimensional system of forces by the example of an upper berth in a passenger railroad car. Let us draw a sketch and make a statement of the problem. A uniform berth is being held in a horizontal position with hinges in the points A and B and with a chain attached in the points C and D. The chain tension and the reaction of hinges are to be found. Let us build a free body diagram. Imagine the constraints removed and the reactions being replaced with the corresponding reactions. The constraints for the berth are the hinge in the point A, the hinge in the point B, and the chain, which holds the berth in the point C. The reactions of the hinges can be resolved into three components: XA, YA, ZA, and XB, YB, ZB. The reaction of the chain is directed along the chain from the point C. Besides, an active force P is acting on the berth. P is the gravity which we apply from the intersection of the diagonals. Thus, we have obtained a three-dimensional system of forces under which the body is in equilibrium. Let us write down the system as XA, YA, ZA, XB, YB, ZB, S, and P. For equilibrium of a body under an arbitrary three-dimensional system of forces, we have to write down 6 equations. 3 equations for the projections on the axis x, y, and z of all forces acting on the body, and 3 moment equations.
Для равновесия произвольной пространственной системы сил нужно составить 6 уравнений.
The sum of projections of all forces on the axis x must be equal to 0, the sum of projections of all forces acting on the body on the axis y must be equal to 0, and the sum of projections of all forces acting on the body on the axis z must be equal to 0. And 3 moment equations. The sum of moments of all forces acting on the rigid body with respect to the axis x must be equal to 0. The sum of moments of all forces acting on the body with respect to the axis y must be equal to 0, and the sum of moments of all forces acting on the body with respect to the axis z must be equal to 0. Let us work out these equilibrium equations. To provide an easier way of solving the problem, let us resolve the force S into 2 components. The projection onto the plane xy as xy with the projection being equal to s multiplied by sine alpha, and the second component as z, which is the projection onto the axis z being equal to sz equals s multiplied by cosine alpha. Let us write down the equilibrium equations. On the axis x, we project the reactions XA, XB, and S, with S multiplied by sine alpha being the component as xy. Onto the axis y, we project the components YA, YB, and the force S.
на ось Z
Onto the axis Z, we project the components ZA,
ZA и
ZB,
ZB,
and the force
сила
P,
P
and the reaction
и
S,
реакция
which
S.
projection is S multiplied by cosine alpha. Now let us write down the moment equations. The moment of forces XA, YA, and XB, YB with respect to the axis X is equal to 0, because the lines of action of these forces are parallel to or cross the axis. The moment of the component ZA is equal to the product of the force magnitude and the distance from the axis X to the force's line of action.
до линии действия силы.
The moment of the component ZB with respect to the axis X is equal to the product of the force magnitude and the distance from the axis X to the force ZB line of action. The moment of the force P with respect to the axis X is equal to the product of the force magnitude and the distance from the axis X to the line of the force's action. In our case, this distance is equal to OE divided by 2. The minus sign in the equation is used because of the fact that if we were to look towards the axis X, then we would see that the force P was tending to turn the body clockwise. Let us write down the moment equations for all forces acting on the system of forces with respect to the axis Y. The moment of the components XA, YA, ZA, XB, YB, ZB with respect to the axis Y is equal to 0. Because the lines of actions of these forces are parallel to the axis or cross the axis. The moment of the component P with respect to the axis Y is equal to the product of the force magnitude and the distance from the axis to the line of force's action. The moment of the force S is determined as the moment of the two components SZ and SXY. Because the component SXY crosses the axis Y, then its moment with respect to this axis is equal to 0. The moment of the component SZ is equal to the product of the magnitude of the component and the distance from the axis to the line of action of the projection. In the equation, the moment of force is written down with a minus sign, because if we were to look towards the axis Y, we would see that the force SZ was tending to rotate the body clockwise. Let us write down the moment equation for all forces acting on the body with respect to the axis Z. The moment of the forces YA, ZA, YB, ZB, and of the forces P with respect to the axis Z is equal to 0, because the lines of actions of these forces are parallel to the axis or cross the axis. The moment of the component XA is equal to the product of the force magnitude and the distance from the point O to the line of the force's action. The moment of the component XA is written down with the minus sign, because if we were to look towards the axis Z, we would see that the force is tending to turn the body clockwise. The moment of the component XB is equal to the product of the magnitude of the force XB and the distance from the axis to the line of the force's action. It is also written with a minus sign, because if we were to look towards the axis Z, we would see that the force was tending to turn the body clockwise. The moment of force S with respect to the axis Z is equal to the moment of the component SXY because the component SZ is parallel to the axis Z and its moment with respect to the axis Z is equal to 0. So let us write down the magnitude of the component SXY multiplied by the distance from the axis to the line of the component's action. This is a perpendicular. From the point O, we draw the perpendicular down to the line of SXY component's action. This perpendicular is equal to the product of the distance OC and sine beta. Sine beta and cosine beta, which we have used for writing down the equation, are defined from the triangle. We have obtained the system of 6 equations with 7 unknowns. Let us count the unknowns: xa, xb, ya, yb, s, za, and zb. This problem is statically indeterminate. To render the problem statically determinate, let us find the resultant reaction along the axis y. Substituting the numerical values, we thus find the unknowns.